Dear all, thank you for joining us today, and we are Group 6 from Lecture Group 4 of the Operating System course. We are here to present our project to analyze the best time quantum of job list 6 by implementing the round-robin algorithm in C++ language. Allow me to introduce the group members who have worked passionately towards the success of this project. I am HIEW, and it's my pleasure to tell you which is the best time quantum for our job list and evaluate it. Next, BALAKUMAARI will demo the code by entering different time quantum, and SHAWN will show how we get the calculation results in the code. Lastly, CHIENG will compare the performance of different time quantum, and NISSHALINY will shed light on the explanation and justification.
My name is BALAKUMAARI, and now I'll be showing how to do the round-robin scheduling program. The program menu offers options to start the round-robin scheduling, which is option 1. Choosing option 1 triggers the algorithm which reads data, initializes arrays, and sets job details. Now let's see the output without diving into the specifics for each time quantum. So I'll be choosing 1. Now I'll be entering time quantum 5. So the processes actually are quite similar, so we won't have to delve into details. As you can see, it displays scheduling details for each job and calculates the average waiting time, average turnaround time, total interrupts. Now let's just press 1 again. Then this time we have to do the same thing for all the other time quantums. Now 10 displays the similar process, but then it 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 outputs a different results, as you can see. So we will just continue for the other time quantums. As you can see, it prompts the user to run the program again. In this case, you just press 1, yes, then press 1 again. Okay, 20, 5, 30, 35, 40, 45, 50, 55, and lastly 60. The explanations for the calculations will be explained by Shawn. Thank you. My name is BALAKUMAARI.
How to get calculation result in the code. First, we're reading data from files. We get the data from job list g6.txt. After that, we're setting total bus time and job arrival time. We have function to set total bus time for each job. First, we look all the 30 jobs and also look all 122 CPU circuits and I/O circuits. Then we add all 122 CPU circuits and I/O circuits as total bus time. Then we have function to set job and arrival time for each job. We set the data as an array of jobs and then set the data as an array of arrival times. After that, we have function implementing the round-robin scheduling algorithm. We initialization and user input for the time pattern. Then we have the calculation of interrupt incurs for each job. We loop through each job to calculate interrupts and also loop through CPU and I/O circle, and then we calculate data sum for interrupt check. After that, we store interrupts count in an array. Then we calculate remaining time for each job. Remaining times equal total bus time plus interrupts incurs. Then we set process count to total number of processes and we perform round-robin scheduling. So this one is the round-robin scheduling logic. And here we print job details and update the total waiting and turnaround time. Then the last one will be the output the average waiting time and then average turnaround time, and total interrupts. That's all.
So this is the comparison chart for the performance metrics. We have average waiting time, average turnaround time, and total number of interrupts incurred for each time quantum. As you can see, we cannot observe the apparent differences whether which time quantum has the best performance metrics because the number of cycles are close to each other. But when we see the calculation result, it's apparently to see that the time quantum 35 has the lowest average waiting time and turnaround time. Since the total number of interrupts for all time quantum are the same, time quantum 35 has the lowest number of interrupts too.
As mentioned earlier, after comparison, we recommend that time quantum 35 is the best time quantum for job list 6, and we will take the output of it to evaluate. So in the output of our C++ program, the burst time, arrival time, turnaround time, waiting time, and number of interrupts of each job is displayed, and the jobs are arranged according to round-robin algorithm in the table. Additionally, the output also shows the average waiting time and average turnaround time of the jobs for time quantum 35. So the result is then compared with other time quantum to determine which is the best time quantum. Before diving into the explanation and justification, let's revise that the time quantum plays a crucial role in job scheduling and significantly impacts the overall system performance. Now, let's move on to the visual representation of the output. As we observe the bar chart, we can notice that the differences in waiting time and turnaround time between each jobs are relatively small. This indicates that our jobs are being processed efficiently with minimal waiting time and quick turnaround time. While this might suggest an overall efficient system, but it also raises questions about potential areas for improvements. Additionally, the number of interruptions are equal for each job.
Now I'd like to explain about the explanation justification of the best quantum time. So the best quantum time as determined by the job scheduling results is 35. This is due to the fact that in comparison to other quantum times, the average waiting time and the average turnaround time for the quantum time 35 are the lowest at 159,997 and 165,549 cycles respectively. So since the job list is the same, the total interruptions are the same for the entire quantum time, which is 1812. Each process is assigned a specific time slice, which is the quantum time in round-robin scheduling, ensuring an equal CPU usage. So the turnaround time, waiting time, and the total interruptions are crucial factors in determining the best quantum time for scheduling. So the turnaround time is the total time, including the waiting and execution required to complete a process. A shorter turnaround time is preferred for faster task completion, whereas waiting time is the time a process spends waiting in the ready queue before execution. Shorter waiting times imply faster CPU access and increased system responsiveness.